Right.
So friends, in the next few lectures, I will address system of particles and rotational motion. A system of particles which may constitute a rigid body comprising of several particles put together and constituting a rigid body. In the rigid body, we have a perfectly defined and unchanging shape. Perfectly defined and unchanging shape. And distances between the various pair of particles which are a constituent of the rigid body, the distances between the pair of particles in the constituted rigid body do not change. So this is one of the things about a rigid body. The other thing is the motion of a rigid body which is not pivoted or fixed in some way, because in rotational motion you have a fixed axis or a pivot. Then that motion of a rigid body which is not pivoted or fixed in some way is either pure translation. Translation means moving in certain direction such that the constituent particles are not affected at all. So translation, as also a combination of pure translation or combination of translation and rotation. This is a possibility. Translation and rotation. If the body is pivoted or there is a fixed axis, then what constitutes is the last number which I am going to thing which I am going to show, and that is the rotational motion. First and the foremost of the things, the tools that we'll require to master is the center of mass concept, which will start with two particles on a line or three particles on a plane comprising a triangular at the vertices of a triangle, etc. And then we'll define it for umpteen particles, n particles, the system where we'll say that the mass can go to the limits of integration. After doing that, learning about the center of mass of a system of particles, we go for a study of a brief description of the motion of center of mass. And of course, then I define, and we have done so before, we have learned about the linear momentum of a system of particles. That is the vectors P1, P2, P3, P4, they all combine together to give the total momentum of the system of particles. Next item, which we have done already, I have the vector product of two vectors which will be used here now, okay, occasionally. Then I define, and I have already defined, angular velocity, which is omega radians per second, defined as instantaneous angular velocity omega is d theta over dt, radians per second or per second. Now we come to a unique concept of rotational motion, which is an equivalent of the force in the linear motion, which is called torque, and this is tau, whatever you want to call it, tau. It is a vector quantity, and also angular momentum L, which is again a vector quantity. Then we discuss the equilibrium of a rigid body and define the mass equivalent in rotational motion, which is called, like we have a mass in the ordinary, the motion that we have taken, which is the measure of inertia. Here it will be moment of inertia I. Very interesting calculations, very interesting learning, and then I will describe, we will learn about the beautiful theorems of perpendicular and parallel axes. Okay, perpendicular and parallel axes. The theorems of perpendicular and parallel axes, which helps us easily determine the moment of inertia. The moment of inertia is known about some axis, we can calculate it about a particular axis, etc. After we have learned about these tools, I'll say, we should be well versed in, I will discuss the kinematics of rotational motion about a fixed axis. Kinematics, naturally, there are only two dimensions. One is the dimension of length and the other is the dimension of time, like in the earlier case. And followed by that, we will learn about the dynamics or kinetics of rotational motion about a fixed axis, where, like the concept of mass, the concept of moment of inertia will jump into the system. Then after that, we propose to learn about angular momentum. Okay, the angular momentum, rotation about a fixed axis, the rotation about a fixed axis. Okay, the angular momentum. After that concept of angular momentum, we wind up with what is called the rolling motion. Okay, so this is how this set of lectures or classes about the system of particles and rotational motion will go. So for the center of mass introduction to you, I'll just take up the case of two particles having mass m1 and m2 at locations x1 and x2 on the x-axis, like it has been shown over here. And this, I will just tell you that the center of mass of the pair of particles is defined like this. Let us test if we are right or not. Okay, let us see if there is only one particle of mass m1, then what happens? That its center of mass is m1 x1 upon m1, which is x1. If we have another single particle over here, then I can say m2 x2 upon m2. So the center of mass lies at the location of the particle. Okay, let us take x1 and x2 equal to each other. Okay, both the particles are placed at the same this thing. Then you can see that x will become equal to m1 x1 plus m2 x1 divided by m1 plus m2. So that x1 becomes common. Make a quick calculation, and here I get m1 plus m2 into x1 divided by m1 plus m2, and they cancel out, and it again turns out to be equal to x1. So by extension of logic, we say that this definition appears to be okay. Okay, so I'm not rigorously determining for you, but instead I am taking the result, the definition of the center of mass on the x-axis, this line. I have put a orthogonal axis over here, xy axis, only because I will take up later on two particles in the xy plane. Okay, so right now I have to concentrate on this line, and I showed you x1 and x2 over here, and this is the center of mass for which the distance from the y-axis is equal to x. Now let us analyze this, because I said that formulae are there, we must do physics after the formulae are there. Look here. If m1 is equal to m2, then what the result will be that x will be equal to x1 plus x2 divided by 2, which is nothing but the midpoint joining on the line, joining the two particles m1 and m2. The midpoint in the clear, it will be somewhere located over here. Now, if we work at the same mathematics and see that m1 is greater than m2, if m1 is greater than m2, then you think, and you take some numerical values to prove it, that x is closer to x1. It will be on this side. Otherwise, if m1 is less than that, m2, then the center of mass will shift towards m2. It will be closer now to x2. Okay. You can draw a parallel. We can draw a parallel. Suppose there are two charges of the same kind, positive, positive, negative, negative. Okay. Now, suppose I have the two charges lying on this line. This is Q1 and this is Q2. Okay. Then if I imagine a charge, if I imagine a point over here, then the electric field due to this will be in this direction, E1, like this, and the electric field at this point need not have any charge, because the electric field is defined at the force per unit charge. So even if you think of a test charge over here, then you will get this as E2. Okay? If friends, E1 and E2 are equal, this is what is called a neutral point. Neutral point. In the neutral point also, if the two charges are of the same kind and their locations on the x-axis are like this, then we get a point closer to Q1, because this will be equal to Q1 upon R1 square, and this will be equal to Q2 upon R2 square. Okay, so if Q1 is larger, then R1 has to be smaller, otherwise. So this is also happens in the case of electrostatics. A similar kind of mathematics is there. I will tell you one more thing about it. Interesting. If the two masses, as has been envisaged over here, the two masses are the pans of a mizan or balance, and the two masses are equal, they will balance about a fulcrum over here. Okay, the masses are same, m1, you can say this is x1 and this is also x1. I'm sorry, x1. The two lengths got to be the same, but this calls for what is known as the center of gravity, and the center of mass of a system of particles and the center of gravity of the same system of particles is one and the same, provided all ingredients, all constituents of that body, they are in the gravitational field, which is same for all locations. The center of mass and center of gravity become one and the same thing. We will do that, and now you understand that if the number of particles is rather increased to n, m1x1, m2x2, m3x3, mnxn, etc., a large number of particles, n number of particles, I can write the value of x extending my argument from here to here, m1x1 plus m2x2 plus mnxn divided by m1 plus m2 divided by mn, which is summation of mixi, where I varies from 1 to n, and summation of mi over here, where ultimately summation of mi, all the masses of all the particles, like here, is the total mass of the system of particles, which we write over here. Okay. Now we extend the case to 3 particles on the vertices of a triangle, and we see as to what happens to the center of mass and how it is the centroid. So if I extend my definition for 3 particles in a 2-dimensional space, and the particles are in the xy plane, m1 x1 y1, m2 x2 y2, m3 x3 y3, then I can obtain the value of the x component of the center of mass as m1 x1 plus m2 x2 plus m3 x3 divided by m1 plus m2 plus m3, and similarly the y component is obtained by this relation. Well, what I can do here, I have taken the axes of x and y. You can take y and z, you can take z and x, no problem. And similar results for the various component values for the center of mass coordinates will be obtained like this. Now, if all my particles are having the same mass, then it is easy to show from here that x will be equal to x1 plus x2 plus x3 divided by 3, y is equal to y1 plus y2 plus y3 divided by 3, and the particles are just shown in that case as the vertices of a triangle, and the center of mass of this system will turn out to be the centroid of the circle. So this is easy to show, easy to understand, but must remember, if we have a 3-dimensional space, we have m1, m2, m3, m4 like that up to mn, okay, then we find that the x coordinate can be said to be equal to the summation of mixi divided by summation of mi, where I varies from 1 to n, y similarly like this, and z similarly like this. So that means it is possible for us to extend these values to these results, and ultimately next I write that the value of r, the location of the center of mass, will turn out to be, I'll give the next expression. So let us generalize, and when we generalize, we obtain the position vector Ri as xi, which is a scalar component in the I direction, I cap in the x direction, and like this I can write yi j cap plus zi k cap, where I, j, k are the unit vectors in the directions x, y and z respectively. And then we can also write in terms of the components of the position vector of the center of mass. I can take x component, y component, z component, keep them with the unit vectors I, j, k like here, and therefore what I can do is I can define like before that the vector r is equal to mi into vector ri divided by capital M. Okay, so this is these are the results that we obtain in the generalized case when the number of particles may be umpteen, okay, at umpteen locations given by Ri. The center of mass is calculated like this. Now again I go back to the same thing. What happens if the origin of the frame of reference, FOR, capital R, if the origin of the frame of reference in the coordinate system, I have y, x and z, and this is the origin of the coordinate system, and it is chosen to be the center of mass. Then of course, very interesting that this sigma MIRI, this will turn out to be equal to 0, think, and therefore R will also turn out to be equal to 0. I can write, now I want to introduce to you how we calculate the center of mass of a regular body of a regular density, homogeneity being one of the properties. Then I write that the x component will be given by this sigma or all the particles delta mi into xi divided by this, and y is equal to sigma delta mi into yi divided by this, which is the total mass of the system, and z as equal to like this. Okay, and if I say that this our delta m, it is infinitesimally small so that all particles can be taken into consideration, what we get is that sigma mi is equal to integral dm, or all the particles of course. So this I write now as integral m to the power dm, and use the principle of integration, that x to the power of n dx. You remember that this is equal to x to the power of n plus 1 divided by n plus 1, with the big provided that n plus 1, you can write this also, is not equal to 0, or n is not equal to minus 1. So in that case, I can write sigma delta I, delta mi xi, sigma delta mi yi, and sigma delta this mi zi as integration of all the x coordinate with the mass dm, y dm and z dm, and so that what I will get is the value of x is equal to like this integral x dm, which we can carry out with the definitions that are given to us about the body under consideration. Yi is equal to y dm upon m, z equal to like this. Okay, and again, if the origin is chosen as Cm, remember this is a very interesting thing. It is used as a tool. Then I get that R, the vector R, x, y, z is equal to 0. Integral R dm is equal to 0, which means x dm is equal to y dm integral, z dm integral, and this also turns out to be equal to 0. Now, this can be extended for calculation of the center of mass of bodies, geometrical bodies in shape, and other bodies where the density of the particles, density remains unchanged, that is, the particles are distributed homogeneously, and there may be occasion for rigorous calculations when the density of the body under consideration is also changing in time. With distance. So then the complexity comes, but for our level it's enough to understand up to this thing. Now the next item is that the motion of the system of particles is taken and compared to the motion of the center of mass of the particles. Motion, when we say, then we talk about the kinematics, and that is the displacement, the velocity, acceleration, etc., which we'll talk in the next lecture. So thank you very much for being with me, and I again reiterate, in doing physics, what I reiterate is UQVA. So far I've received only small queries. Sometimes people like, very good, this, that. I would like to serve you more. If you interact with me in the comment section, please write your problems and difficulties, and let us solve them, because these are corona times. I'm staying home, you are staying home, you have got the chance to interact with me, and you have a chance to also help me with this, which is what I intend to do for you. Hope this has been useful to you, and looking forward meeting you soon with another lecture, another class in the same system of particles and rotational motion. Thank you very much. Bye.